So we're going to be talking about a very important number that's associated with any square matrix. And essentially chapter 2 in the textbook is dedicated just to this one real number. It's a very important number. You might remember we talked about for any square matrix we can define the trace of a real number, which is the sum of the main diagonal entries. That's a relatively easy calculation to do, but the number that you get, the trace, not as powerful, shall we say, as this number called the determinant will be. However, calculating the determinant, we will see, begins to be very difficult to do and very costly to do, especially for larger size square matrices. So we're going to talk about in this section, first of all, a method known as cofactor expansion, but we're going to build up to that. So the determinant, and this is the way it's spelled here, is a real number, again, associated with any square matrix. The notation we use is DET for determinant, within the matrix there in the parentheses, finding the determinant of the matrix A, or, and this is very important here, or we use absolute, sort of like, well, I say absolute value bars, vertical bars, right? This is not absolute value. I mean, we don't have the absolute value of a matrix here. This is the determinant of a matrix. So that's an adjustment you need to make. So when we're talking about real numbers, obviously the vertical bars mean the absolute value. For matrices, square matrices, it means the determinant. Okay, we'll start with off easy for a 1-by-1 matrix. Obviously, it's just a real number. In that case, the determinant of the matrix is equal to that real number. So need to be a little careful here. Let me look at the 1-by-1 matrix B, which again is just a real number. It's just -5. However, the determinant of B, which we could write, as I said, this way, all right, is equal to what? The actual entry, -5. Now some of you look at that and say, wait a minute, that doesn't look right. Absolute value of something. Well, remember, it's not the absolute value. So again, the determinant can be a negative number. It could be any real number. It could be 0, a positive number, or a real number. It doesn't have to be an integer only. It could be any real number. Okay, so that's pretty easy. The determinant of a 1-by-1 matrix, no problem. Which, by the way, I'll just say for a 1-by-1 matrix, the trace and the determinant are equal. That's the one time that they are equal. Well, I shouldn't say that only the time they're equal. There are special cases where they will be equal for larger size matrices. Let's go to the next level, 2-by-2 matrix. Okay, so if A is a square 2-by-2 matrix, the determinant of A, which can be written either way. Also, you'll write it this way sometimes. So notice here we've got vertical lines and we've written out the entries of the matrix. Okay, so when you're writing a matrix, you have to use brackets or parentheses. Now, there's a couple of you that like to write just vertical lines because it's difficult for you to write this little indentation here, I guess. So you say, I can't do that. That's too much trouble. Okay, well, I'm sorry. You're going to have to go through the trouble. If it's a matrix, brackets or parentheses. If it's a determinant, then vertical lines. You can't have vertical lines representing a matrix. This is not a matrix, it's a real number, but it's indicating we're taking the determinant of course, this 2-by-2 matrix that's inside. So this whole thing is a real number. So we use these notations, and look what the actual computation is here. The entries A times D minus the entries B times C. And this should look familiar from something, all right? A times D you can think of as the product along the main diagonal, looking at the product there, minus what? BC, which is the product of sort of the off diagonal entry. So you got AD minus BC going that way. And this quantity you probably remember from the formula for the inverse of a 2-by-2 matrix. And we'll get back to that at the end of chapter 2 and explain the connection there. Okay, so if we say a matrix C is this matrix, then what is the determinant of C? Well, we've got A, which is 3, times D, which is 2, minus BC, 4 times negative 7. So I get 3 times 2 is 6, minus 4 times negative 7, that's a negative 28. 6 minus negative 28 is 6 plus 28, which I believe is 34. So there's the value of the determinant. So here, the determinant up here was a negative number. Here it's a positive number. Again, it could be 0. Now, most of you probably recognize the DET from playing around with the calculator's matrix row operations. And let me just show you. If I go into matrix and over to edit and do a 2 by 2 matrix where I have this matrix entered in, let me do that. 3, enter, 4, enter, negative 7 and 2. There's my matrix there. Let me get out of that. And then I'm going to go back into matrix, and under math I'm going to go to, well, it's right at the top. So that's why I'm saying a lot of you probably already have seen that. Some of you knew what that was, and if not, now you do. That is indeed the determinant. So I can now take the determinant of that matrix A, and of course it's going to give me what I asked it to. Okay, so it will do square matrices in the calculator, 2 by 2 and higher, 3 by 3, 4 by 4, and so on. But we've got to explain how to go about doing the determinant now of a 3 by 3 matrix. How does the calculator do it? Well, let's at least talk about how we can do it, because we're not going to just be number punchers. And so make sure you understand how to compute a 2 by 2 determinant. It's going to be very important. So let's go to the next level. Before we do so, though, we have to define some terminology here. And so this is called, we're going to be talking about determinants calculated by what we call cofactor expansion. So we have to describe and to give you the definition of the cofactor. So if we have a square matrix A, first of all, we want to define something called the minor of every entry. So the minor of the entry, remember this is A sub ij, so this is the entry in the ith row, jth column of the matrix capital A. Okay, so the minor of that entry is denoted capital M subscript ij, and it's defined to be the determinant of the submatrix that remains after the ith row and jth column are deleted from A. Okay, and we're going to show you how to do that here in a minute, so if that doesn't make sense, but we're going to eliminate the row and column that entry is in and find the determinant of that corresponding matrix. We call it a submatrix because it's going to be if A is, say, 5 by 5, the submatrix will be 4 by 4 because we're removing one row and one column. We're going to stand by the definition that the minor is the actual determinant. Some textbooks and sometimes they'll talk about the minor being the actual matrix, the submatrix you get, and then you take the determinant of the minor. But we're going to say the minor is actually the determinant of that submatrix. Now we're ready to define the cofactor. The cofactor of any entry in a square matrix is denoted capital C, right? So the ijth entry of matrix A, its cofactor is capital C ij, and it's defined this way: -1 to the I plus j power times what? This minor. So notice when I take -1 to any power, I'm either going to get what? -1 if I plus j is an odd number, or +1 if I plus j is an even number. And that means that the cofactor is either going to be equal to the minor or equal to -1 times the minor for the corresponding entry. Okay, so let's talk about how to do it then. Let's see if this makes sense. Let's find, for this square matrix A right here, let's find M32. So it's going to be the determinant of the submatrix that we get by removing the, in this case, third row, second column, because this is M32. Now if I go to the third row, second column, we're looking at that -2. Now it's real important here to realize that this -2 is not going to come into play with the calculation of the minor, because we're removing the row and column that it's in. So I'm going to take out that row and I'm going to take out that column, and what do I have left? See those 4 entries? I'm going to collapse down to create a 2 by 2 square matrix, and I want to find the determinant of that matrix. So notice the entry we're looking at, third row, second column, right? Remember, it's always row first, then column. You got to get that down. It's not column then row. It's row 3, go down third row, second column over -2. But that -2 is not going to be in the calculation at all. at all. So that's real important. Okay. So this is going to be the determinant of, right? So vertical lines, -1, 7, -5, 4. So I can do this, right? 2 by 2 we just talked about. So AD is -1 times 4 minus BC, -5 times 7. And we get -4 minus a -35. -4 plus 35 is 31. Okay. Let's take a look at M22. Okay. M22 sounds like I'm a ballerina or something. M22. Okay. Second row, second column is at 0. So I'm going to remove that row it's in and that column it's in. See if we could do this. And you see the numbers left are the numbers in the four corners, so to speak. We're going to collapse those down, and that will form the matrix, the submatrix, if you will, that we're going to find the determinant of. Okay, again, I can find this determinant, the AD minus the BC, -8 minus a -15. -8 minus a -15. -8 plus 15, which is 7. Okay, and so on. So I can find 9 different minors, right? I can find M11, M12, M13, M21, M22 as we did, M23, and so on, right? So make sure you understand how to find those minors. So if I'm finding, say, M33, finding the minor for this entry here, I'm going to remove that column and that row, and that resulting submatrix, I'm going to find the determinant of that. That's going to be M33. Okay. Well, let's now find C32. So what's that? That's the cofactor, and the cofactor we said is just -1 to the I plus j times the actual minor. So C32 is going to be -1. I is 3 in this case, and j is 2. All right, so it's to the I plus j power times M what? 32. Okay. Well, this will be -1 to the 5th power. M32 we already calculated, so we'll just write that down times 31. But -1 to the 5th power is a -1, because -1 to an odd power is -1, right? And so I'm going to get -31. C22 is -1. I and j are both 2. So I get -1 to the 4th times M22, which we calculated to be 7 there. -1 to the 4th, though, is +1, right? So -1 to an even power is going to be +1, so I just get 7. So you can see the cofactor sometimes is -1 times the corresponding minor, and sometimes it's equal to the minor. Okay. Now the sign, that we get, I'll say this -1 to the power sign, right? Of course, it depends if the minor was negative here. It was -31. Of course, the cofactor would be positive. But that sign that we get from this -1 to the I plus j, we can see a pattern, right? If we're in the first row, first column, right? I and j are 1. 1 plus 1 is 2. It's going to be -1 squared, so it's going to be positive, right? +1. If whereas for I is 1, j is 2, 1 plus 2 is 3, -1 cubed is negative, right? 1 for I, j is 3, 1 plus 3 is 4, -1 to the 4th, positive, and so on, right? But you can see this pattern develop, right? And so basically, if you're somewhere in the matrix and you're trying to find what's the sign of that -1 to the I plus j, you start with positive in this first corner, and every time you move, you just change the sign: negative, positive, negative, positive, negative, positive, and so on. And you can find the sign for that -1 to the I plus j. And that is helpful to think about later on. Okay, so now that we know what a cofactor is, so if I have a 3 by 3 matrix, there are a total of 9 cofactors. There's a cofactor for every entry. And remember, the entry itself doesn't come into play with the value of its cofactor. All right, so with that, we're now ready to talk about cofactor expansion. So the determinant of an n by n matrix can be computed by the method of cofactor expansion. So what is this method of cofactor expansion? All right, this method is, first of all, we can say along the first row. That's one way of doing it. And the determinant in that case is going along the first row, take the first entry in the first row, which is A11. So take that entry and multiply it by its cofactor. Then take the second entry in row 1 and multiply it by its cofactor. And the third entry in row 1 and fourth entry, all the way to the nth last entry, right? So this is n by n. The last entry will be A1n times its cofactor. And add them all up. In summation notation, we can write it this way. So this is the determinant using the method called cofactor expansion. We multiply the entry by its cofactor, and then we add them all up. Now, here's the thing that's interesting. That sum, when you multiply those entries by their cofactors and add them all up along the first row, you'll get the determinant of that matrix. But you will also get it along any row if you do the cofactor expansion. So if I go the second row, take the first entry in the second row times its cofactor. Second entry in the second row times its cofactor, all the way to the last entry in the second row times its cofactor. Add them all up, you get the same number. In fact, along the ith row, right, what will the determinant be? It'll be first entry in the ith row is AI1 times its cofactor, plus the second entry in the ith row is AI2 times its cofactor, all the way down to the last entry in the ith row, which is AIN times its cofactor. And this is equal to, in summation notation, the summation for J, and I'm using J because we're going across a row. That means the column is changing, right, as we go across from column number 1 to column number n, so to speak, right, of what? A, I, J, C, I, J. Okay. All right, but that's not all. Okay, it's like the Ginsu knife commercial. But wait, there's more. We can do cofactor expansion along the first column, which is take the first entry in the first column, which is A11 times its cofactor, second entry in the first column, right, second row, first column, times its cofactor, all the way down to the last entry in the column times its cofactor. If you do cofactor expansion along a column, guess what? You get the determinant as well. And you can do that along any column. If I do it along the jth column, the determinant of A is going to be what? The first entry in the jth column is A1j, first row jth column, times its cofactor, plus the second entry times its cofactor, all the way until the last entry, which will be the nth row, whoops, ANJ, CNJ times its cofactor, right? Which again, this will be the summation. Now we're going down a column, so we're summing over the rows. I equal 1 to n AIJ CIJ. Okay. So here's a very interesting thing, okay, that I can do this procedure, and along any row or any column I get the same number, which is called the determinant of this matrix. That's a pretty amazing thing. Now I'm not really going to well, I'm going to show that this works actually for our 2x2 case. So let's show this, that this works for 2x2 case, because we already know what the determinant is for the 2x2 case. Let's see if this gives us the same thing. All right, so let's look at the determinant of a 2x2 matrix. We know what it's supposed to be, and the way I'm going to do that is I'm going to do cofactor expansion along the first row. So we can go along the first row, first column, second column, we'll get the same thing. So I'm going to do cofactor expansion along first row. So what is that? That's A11. What's the first entry? That's A. So that's the A11 times its cofactor, right? C11. So what's the cofactor of A? So remember what we do. We remove, first of all, find the minor, remove the row and column that A is in, and we're left with what? Just the 1 by 1 matrix D. 1 by 1 matrix D. So what is the determinant of a 1 by 1 matrix? It's just the entry. It's just D. Okay, so we get D. And then don't forget the cofactor is what? -1 to the I plus J. Well, we're in the first row, 1, 1. We're in the first row, first column. So that's going to be -1 1 plus 1 squared times d. So that's negative 1 squared is positive 1 is d. So we get d. Well, that's good. That's the AD. And then I add the second entry in the first row is C. So that's the A12 entry, right? Times its cofactor C12, which is going to be what? Negative 1 to the 1 plus 2 cubed times its minor, and its minor is what? To take out C and take out the row and column C is in rather, and we're left with the 1 by 1 determinant B. So the determinant is B, so the minor is B. All right. And negative 1 cubed, though, is a negative number, so we get negative B, and that is the answer there. But what is this then? AD plus what? C times negative CB or negative BC. AD plus a negative BC is AD minus BC. And it checks, right? It checks. It does work for the 2 by 2 case. And I'll challenge you to do this. Do cofactor expansion along the second row, or along the first column, or along the second column, and show that you get the same thing all three ways. Okay, which you will. Okay, so now that we know cofactor expansion, let's move on to find the determinant of a 3 by 3 matrix. Okay, I'm going to go ahead and show you two ways. I'm going to go along row 1 first of all. And so the determinant of A in this case is A11, so I'm going along the first row, so negative 1, 10, negative 5. I take that entry, negative 1, so that's my A11 there. And then I've got times its cofactor. Cofactor is negative 1 to the I is 1, j is 1, 1 plus 1, times the minor, which is the determinant of the submatrix obtained by removing the row and column that our entry is in. Our entry is in the first row, first column, and you can see that 2 by 2 matrix that we get. Okay, so again, this right here is our minor. The determinant of this matrix is our minor M11, and then the negative 1 to the 1 plus 1 times our minor, that's our cofactor C11. Okay. Plus, so that's the first entry times its cofactor, plus the second entry, which is 10, times its cofactor, which is going to be negative 1. We're now in the first row, second column, so I is 1, j is 2, times its minor, and of course its minor is, pull out the first row and that second column, and we get the power t. There's our power t right there. And we can crunch down and we see our 2 by 2 matrix, 7, 4, 3, 8. 7, 4 across the first row, 3, 8 across the second row. All right. And then last but not least, we add the last entry, which is negative 5, times its cofactor, which will be negative 1. Now we're in the first row, third column, so I is 1 and j is 3, times its minor. We're going to remove that row and column there, and we're left with 7, 0, 3, negative 2. Okay, so there's the setups. Hopefully everyone understands that. And now we just crunch it out. We're just a number cruncher, so to speak. I get negative 1. Negative 1 squared is positive 1. I'll just put the positive 1 here. We know it's not going to affect anything, but just to remember that's where it's coming from. Times this, which is what? AD, 0 times 8 is 0, minus BC. Be careful here. Minus what? 4 times negative 2, minus a negative 8. That's the first calculation. Plus 10. Negative 1 to the third is negative 1, and then our determinant here is 7 times 8 is 56, minus 3 times 4 is 12, and then plus the negative 5. Negative 1 to the fourth power is positive 1, and then our determinant 7 times negative 2 is negative 14, minus 3 times 0 is 0. Okay. And just what do we get then? Negative 1, 0 times a negative 8 is positive 8. 8 times negative 1 is negative 8. Here I get 56 minus 12. That's 44. Negative 1 times 44. Negative 44 times 10 is negative 440. and then I get negative 14 here times negative 5, negative times negative positive, 5 times 14 is 70. And if I add all these up, I get negative 378. There's the determinant, and it's negative. Again, the determinant can be any real number. Okay. Again, you can check with your technology, obviously, but we understand that hopefully how this process works. Okay, so now we want to take a look at cofactor expansion. I want to do cofactor expansion along a different row or column. Okay, and if you look at this, there's one row, or there's sometimes even though you get the same thing expanding along any row or any column, you'll get the same number. You'll get this negative 378. Sometimes it helps to choose a row or column that kind of has some more helpful things in it. And one of the helpful things is if we have a zero entry in the matrix, and we have one right here. What's going to happen there? If I have a zero entry, we're taking the entries and multiplying by their cofactors. Well, that zero entry essentially tells us that we don't even have to calculate the cofactor, because 0 times any cofactor, whatever number we get, is 0. So we kind of like that. It kind of speeds things up a little bit. So let me show you. I'm going to do cofactor expansion actually along the second column. Let me do this in a different color here. So I'm going to go along column 2. So I'm going to go along column 2. And so column 2, we got 10, 0, and negative 2. So first of all, the first entry in column 2 is 10, and that's in the first row, second column. So it's negative 1 to the 1 plus 2. In fact, it's going to be identical to this one we did up here, right? Because again, I do the power t thing, right? Take out that row, take out that column, and 7, 4, 3, 8, just like we had there. So that's the same. But here's where the fun part is, right? The second entry is 0. Going down that second column, the second entry is 0. So we just have a 0. I'm not going to compute the cofactor because 0 times anything is 0. And then plus what? The last entry. Now we'll do that one, which is a negative 2. And that is in the third row, second column. So I've got 3 plus 2. And then its minor is, right, for negative 2, take out that bottom row and this middle column, we got the inverted t, okay? The inverted t. There we are. And negative 1, negative 5, 7, 4. Okay. And we'll just do the calculation here. This one we already did above. It was 10. Negative 1 cubed is negative 1, and we did 56 minus 12. That was 44. So I'm just going to re-put that in there. All right. Plus, of course, that's 0. And then we got negative 2. Negative 1 to the 5th power is negative 1. And then here I got negative 4 minus a negative 5 times 7, negative 35. So be careful, subtracting sign numbers. I've seen people, mess that up, so be real careful. Of course, negative 4 minus negative 35 is negative 4, plus 35 is positive 31. And so I get negative 440 here. Here I get positive 2 times 31, that's positive 62, and negative 440 plus 62 is indeed negative 378, which is the same thing we got doing it along row 1. And so I would encourage you to try maybe cofactor expansion along row 2 or 3 or column 1 or 3 and just confirm that that is the case. Okay. So in general, in doing the determinant of a 3 by 3 matrix, doing cofactor expansion, we've got 3 2 by 2 matrices to find. But if we do have zeros in the matrix somewhere, we can sort of cut that down, right? But in general, if there's no zeros in the matrix at all, we're going to have 3 2 by 2s. Okay. Well, let's talk about a 4 by 4 matrix. What's the determinant going to look like there? Well, let's pause this video, and in the next video we will take a look at that.